Welcome to the Explainer. Today, we're going to go on a builder's journey. We're going to break down the exact blueprint data scientists use to turn a simple idea into a powerful predictive model step by step.
All right, let's jump right in with a big question. When you think about some powerful AI, do you picture, a lone genius having a eureka moment? Or is it something a little more methodical? How do these things really come to life?
Well, here's the thing. Creativity is absolutely part of it, for sure. But building a successful model, it's way more like being a master architect than some mad scientist. It's all about following a solid blueprint, a structured, logical process that, honestly, anyone can get their head around.
So, let's pull back the curtain and look at the entire blueprint for this journey. Think of this as our map, the high-level guide that's going to take us from A to Z.
Okay, so here it is. This 5-step process is our guide. It literally takes us all the way from just a question, an idea, to a real-world tool that actually works. We'll start with defining the problem, then get the data ready, pick and train a model, check and tweak it, and finally, get it out there and keep an eye on it.
All right, let's tackle step 1, laying the foundation. And this is so crucial. I mean, think about it. An architect's blueprint is just a piece of paper without a solid foundation, right? It's the exact same thing here. A machine learning project is doomed to fail if you don't have a super clear, well-defined problem from the get-go.
Seriously, before you even think about writing a single line of code, you have to nail down exactly what problem you're trying to solve. This, right here, is where so many projects fall apart. If you don't have a crystal clear problem definition, you could end up building a model that's technically perfect, but completely useless in the real world.
So, the key here is to get really specific. First, you define the task. Is it classification, putting things into buckets, or maybe regression, predicting a number? Then you need a clear business goal, like, say, predicting which customers are about to churn. And maybe, most importantly, you need a metric. This is your speedometer. It tells you if you're actually succeeding. Are we shooting for 95% accuracy? You have to decide that on day 1.
Okay, now we get to the part that, if you ask any expert, they'll tell you is the most important part of the whole journey. It's time to get our hands dirty with the data. Believe me, this is where most of the heavy lifting happens.
And I absolutely love this analogy. Think of it like this. You could have the fanciest, most high-tech oven on the planet. But if your ingredients are junk or you haven't prepped them right, your final dish is going to be a disaster. It's exactly the same with machine learning. You can have the most brilliant algorithm, but it's totally useless without clean, well-prepared data.
Now, a huge part of this prep work is something called feature engineering. This is where the magic really starts. It's all about using your domain knowledge, what you know about the subject, to create new, more powerful variables from the data you've already got. It really is like a chef creating a custom spice blend to pull out all those hidden flavors.
But here's a catch. Models only speak the language of numbers. So what do you do with something like color? You can't just feed it the word red. You have to encode it. One method is one-hot encoding, which basically creates a new on-off switch for each color. Is it red? Yes or no? Super clear. The other way, label encoding, just slaps a number on it. 1 for red, 2 for green, 3 for blue. Now, that's way more efficient, but it can accidentally trick the model into thinking blue is somehow more than red, and that can really mess things up.
And this is such a great way to see what one-hot encoding actually does. Look at that. That one color column gets blown up into 3 new columns, red, green, and blue, each with just a simple 1 or a 0. Now that is a language a machine learning model can easily understand and work with.
Okay, but what happens if your data is totally lopsided? Imagine you're trying to predict a really rare disease and like 99% of your data is from healthy people. The model might just get lazy and learn to always guess healthy to get a good score. So to fix that, we've got a few tricks up our sleeve, like making more copies of the rare cases, that's upsampling, or getting rid of some of the common ones, which is downsampling. We can even create new synthetic data points.
And this chart just shows it perfectly. The goal is to go from a data set that's all skewed to one side into something nice and balanced, where both things we're looking at are represented pretty equally. This gives our model a fighting chance to actually learn the patterns for both outcomes, not just the one that shows up all the time.
So once our data is clean and balanced, you can't just throw the whole thing at the model. Nope, you gotta be smarter than that. We split it into 3 separate piles. We have the training set, which is what the model learns from. Then there's the validation set, which we use to tune its settings. And finally, the test set. This part is sacred. The model has never seen it before. It's like the final exam, totally unbiased and honest.
A pretty standard way to do this is a 70-15-15 split. So, a big 70% chunk for training, 15% for validation, and that all-important 15% that gets locked away in a vault as the test set. This way, the model has plenty of data to learn from, but we also have these independent checks to make sure it's not just, memorizing the answers.
Okay, our ingredients are perfectly prepped. Now it's time to actually start cooking. We're moving into the training and testing phase. This is where the model finally gets to sink its teeth into the data we've worked so hard to prepare.
A question I hear all the time is, so which algorithm is the best one? And the answer is always, well, it depends. There's no silver bullet. The right choice isn't about finding the most complicated, fancy algorithm. It's about finding the one that's the right tool for the job. The one that fits your data, your computer power, your deadline, and what you're actually trying to do.
So the model gets into this really important loop. First, it trains on the data. Then we check its homework on the validation set. Based on how it did, we go back and tweak its hyperparameters. Think of these as the high-level knobs and dials that control how it learns. And we just keep repeating that loop. Train, check, tune, repeat, until we've squeezed out the best possible performance.
All right, we're in the home stretch. For our final section, we're taking the model out of the lab and releasing it into the wild, the real world. This is the moment a data science project stops being a project and starts being an actual product.
Deployment. This is the finish line, right? It's that exciting moment when we plug the model into a website or an app or some business process, and it finally starts doing its job, providing real value by making predictions on brand new, live data.
But wait, the journey is not over at deployment, not by a long shot. Releasing a model into the world comes with some pretty huge responsibilities. We have to keep a close eye on it, constantly asking questions. Is it fair? Is it transparent? Has the real world changed in a way that's making its performance drift? And are we protecting people's privacy? These aren't just one-time checks. They are a continuous, ongoing part of the model's entire life.
So if you remember just one thing from this entire builder's journey, let it be this: a model's success, its accuracy, its reliability, all of that is decided long before anyone ever hits the train button. It all comes back to the data. It's all about thoughtful, careful data preparation. And that leaves us with one final, big thought to chew on. As these AI systems get more and more powerful, maybe our most important job in this new world isn't just being the builder. Maybe it's being the master chef, carefully, thoughtfully preparing the food for thought that will ultimately shape the intelligence of these systems.